use of steel in the structural industry. It is very true, but it's not the only material, of course, that we consider a useful structural material. So just by contrast, today we'll talk mostly about plastics. And it's not that I don't want to talk to you about other things. Spent the week at the largest pipeline conference. We have about 3 million miles of pipelines in the ground in the US. So I know you're used to numbers. Maybe for dollars that's not too bad, but I'm sure you know your geography and the size of this country. 3 million miles is a lot. So today we'll talk about plastic, and I'll give you some background information, a little bit the structure, a little bit how it fails. But when I come back next week, I do want to talk to you about pipelines because they've been in the ground for so many generations. You know, we've been expanding that network, and the specifications for materials have changed over time. So that's a little bit how we're going to transition in the course from talking about material selection into really talking about how you specify material, how you verify they're good, and whether you need to go after the fact and find out if they were what they were supposed to be, which is a little bit what's going on with those pipelines. I think we all know nobody really wants a new pipeline in their backyard, but everything that's existing is being used. It used to be primarily steel. It is steel nowadays for large pipelines, for transmission pipeline that goes interstate. And those we have 300,000 miles. I mean, it's just a lot of steel. So that should be interesting. It will be next Thursday. So in terms of the class schedule, Monday's off. So Tuesday next week is going to be Professor Eager. Wednesday as well. I'll come Thursday. And Professor again on Friday next week. So that's our schedule. I'll post it, but just so we all have it here as well. The plastics. Oh, yeah, let's just do plastics. Skip all that. You may know a few of them, like polyethylene, that's used for even the grocery bags and all sorts of things. It's a very, very simple. Do you guys see the screen? Is that, yeah, okay. It's a very, very simple polymer structure, and that's why it's very, very deformable. So the main difference when you go from a polyethylene to polystyrene, which doesn't have too much deformability, is the size of that side group that is not on the main chain of the polymer. So polyethylene, it's just hydrogen that is on the side. Over here, you have an entire benzene group. That's pretty hard if you try to slide two chains relative to each other. That's a network of 6 other carbons here trying to prevent that from going on. So in between, you have all sorts of combinations. So the polypropylene's got 1 carbon to the side here. Okay, yeah, so that makes a difference. So polypropylene is a little stronger. It doesn't deform as easily as polyethylene. PVC, this one here is also very, very common. And the chlorine makes it, you know, with a certain amount of ionic charge, so it's not, again, as deformable as the polyethylene. Now, in the context of when I did introduce a little bit the materials in the first week of class, I said, you know, a lot of these will be semi-crystalline. I showed you the spherulite structure and all that. We have it here again. And all that chemistry here is affecting how you will crystallize. So if you're the poly styrene here, it's going to be pretty hard to turn into a network of little layers of crystals with amorphous zone. It's because it's harder to make that movement. So on the extreme, just going back one more time here, the polycarbonate, so what we use for glasses, you see it's got a lot more complex molecular structure, and therefore it doesn't crystallize. And that's why it's transparent too. But all these things end up being related. And what I worry sometimes is, and that's the advantage, I guess, of giving you just a summary, is hopefully you remember the bottom line. If we could do a 12 lecture on polymers and then get into the detail, but forget about the main item. I mean, the main item is you do need to know a little bit about the molecular structure. As a good engineer, it gives you some sense for what it looks at the microscopic level and how it's going to behave in service. So if you remember here, the idea was everything is melted. So everything is amorphous, disorganized. It's essentially controlled by probability, randomness. Eventually, you get to a point where you start crystallizing here in the nucleus of this, and then it starts growing in different directions, just a little bit like a snowflake or a little bit of a ice formation on a piece of glass. It starts and then spreads in different directions. Now, sometimes if something is injection molded, like this piece here, it stays like that. This has the spherulite structures inside of it, and therefore it's fairly low strain. This one piece was the connector for the gasoline line on a jet ski type device. So you just go in the water, you put the fuel in, put the cap. So this is essentially gasketed to the hull, and then you got a back screw here to hold it in place. You put it to a big pipe, and hopefully when I circulate it around, you'll see I don't really like it because it's just not a whole lot of plastic as opposed to the size of the pipes. This was actually kind of an issue. It was in service for a number of years, but there was some concerns, to say the least, about the long-term longevity of that. So when we have the opportunity, if we want, I didn't bring the pipe sample. Next time. For pipes, a lot of time they are extruded, so they essentially are cast into this spherulite structure, and then the next step is to draw it. That's what you have nylon cords for too. So this is really in a schematic, again, trying to make sure you'll remember for a while, hopefully forever. You have the spherulite, and of course, initially it's a little bit of a viscoelastic behavior in the case of polymer, and we'll go to that. You don't have to worry about that. So it's going to deform a little bit. Eventually, it starts yielding. So what's unique with the plastics, a lot of times, instead of having that stress-strain curve for steel, so I'll draw a steel one. This is appropriate right here. So for steel, you have that elastic behavior. It's very, very stiff, so this actually magnifies. Then you have what we call the yield point. It starts deforming. It has a strain hardening. You go through the peak. You have neck formation at that point, so the deformation starts to localize right here. And then eventually it fails, just like that. Always. So the main difference with the plastic, because of all this super long molecular structure, is you can have a little bit of a similar behavior. So let's just draw it here. It's not quite to scale, so it's actually softer, right? So let's try to get this a little better. So it's much softer elastically. And you can have it at a decent strain. It is lower, but you go up here, you go back down, and you can go back up again. And then it fails right here. So what happens? Yes?
Is that true strain, or is it engineering strain?
Good question. Very, very good question. this is engineering strain. This is engineering strain because if you had sort of a strain gauge on the material itself, the material always strain harden a little bit. In this transformation from this state to this state, it does continue to harden, even if it's a plastic. Now, the main difference is when you have this neck formation, it's related to an instability, so you don't have enough strain hardening, so when the deformation starts to localize, it continues to happen there. That's what really necking is. When you're not stable against, because when you deform a specimen that's just perfectly flat, you just have the possibility for perturbation. So there's a little bit of an area that gets stretched a little bit more, and therefore the cross section is less, the stress is higher. But what happens initially in this curve for steel is you work harden. So even though now you have less of a section of material, that material is stronger, and therefore the deformation starts to continue in other locations. That zone becomes inactive. So visually, essentially, I'm saying if I have a duck bone specimen here, and I try to deform, and there's a little bit more strain in this section, so A is going down, but the sigma yield or the flow stress is going up. So to the extent that this is going up sufficiently more, the deformation here stops. And I'm deforming now in the other area, the same thing happened. Now, there will be a point where I don't have that much of an increase in my yield stress with deformation. So when I have this little perturbation of a local reduction in the area, it localizes. That's what necking is. So it's still going up, but not enough. It necks. But because you have this fibrillar structure that's starting to take place, there's just so much strain hardening that you reach that point where this is going up through the roof, becomes a lot more rigid, and that neck stops. So what happens in deforming a polymer in tension is you can have the neck formation, so your specimen's going to look, if we just draw this section, literally look like this. Very, very localized. This could be half this thickness. And then the next step is very, very long, tiny specimen. So that neck is growing in the two directions. So when you see a stress strain curve for a polymer, sometimes it'll go to 600% strain before it breaks here, because you form the neck and then the neck just spreads over the entire length. Don't know if we need this too much. Yeah, a little bit. Okay, so we talk about this spherulite and a little bit what's going on in it. There's a lot of transformation taking place. So at the beginning, you start deforming in these shear planes at 45 degrees because you can essentially just be sliding two layers of crystal by deforming the soft amorphous layer between them. Now, you don't have compatibility when you're doing that. You are creating a little bit of tension right at the center. And for some polymer, like polystyrene, that's the place they'll break, because now you've introduced enough tension that you have microvoid formation, and we'll go through that later. So if it wasn't for all this complex structure, you will not start forming voids very easily, but it's this critical stage as you start to transform that typically gets you to trouble. So what we're saying is the plastic can give you 600% strain or 5%. There's not a whole lot in between. It's all about whether it's going to pass this critical stage in step B and C over there. So this is pretty significant. Just to go a little bit more on how the polymer deform, and that's to speak specifically to viscoelasticity. Viscoelasticity, I'm sure you've heard it 5 times. It's very simple. There's really nothing special about it. You want to think about a spaghetti that is really just moving all the time. And then what happens is you have to think about how much it's moving. So first of all, it's not just a straight spaghetti. It's got all these little side groups, whether it's just hydrogen or whether it's a carbon group or the whole benzene group as a side group. So what can happen is to go from here to here is you just realign it a little bit at a very small level. So when we had the carbon-carbon connection, it's going to look like this. This one's aligned, maybe the next one is here, and then it gets disorganized. So you can just rotate this because we're not talking about changing the angle of these connections nor the distance. It's just about twisting it. So just by twisting it, it happens very, very quickly because all these movements are very, very quick at the junction between individual connections. So you get that behavior very quickly. So the elasticity in the case of the plastic is not the stretching of the bonds, which is what the case is with metals. All right, what happened next? Over time, you can have a little bit of a relaxation. So what that means is this chain, let's say there's another coming in another direction. Now, I won't draw it. This gets very complicated. Just by rotating this one, I'll get past. So I'm going to be able to have just a very, very small movement by the rotation of the side group. And now we're talking about a movement between different chains. So that's our second level. And then the third level is, the things just really, really start to creep and move. So the entire center of gravity, if you will, of each macromolecule starts to move with respect to another one. And we call that viscoelasticity. So that's all you got. Any questions on that? Let's talk about that a little bit because, I mean, you could. There's a book. This book by Ward and Hadley is very good for that in the sense that it doesn't focus too much on these little models of dashpot that don't really tell you what's going on in the material. I mean, these are useful because you do need to represent it with an equation, but I mean, there is no dashpot. There's no suspension inside the plastic. Anybody? All right. We'll talk a little bit about applications. A lot of the residential plastics turn gradually to be residential piping is turned to be a lot more plastics. And the reason when you're looking at these coils, and this is a big one, but you can have much smaller one, is you have fewer connections. So you can come with this roll of tubing and you drill some holes through the walls and you go kind of around the house without having to cut to a precise slant, put a elbow and solder all that. So it's very, very quick installation. You only need connection when you're getting to the faucet or the shower valve, those sorts of things. So it's probably been a cost saver at least a factor of 2. I don't want to say exactly, but because I don't know. But the downside then, and one of the issues with that is the connection. So plastics like the one I circulated, you can make them in very, very complex shapes. You have them here, but they're not exactly as resistant, again, because they are cast. So it's easy to make this one in a very robust, transformed state that doesn't have the spherulites in it. But when you cast, you pretty much are stuck with the spherulites. So that's why fittings a lot of times are made of a stronger material, whether it's a metal or a different type of plastic to be able to sustain, first of all, the extra load. Yes?
So what makes these plastics, some of them are reusable, right? You can remelt them
Yes.
and reproduce another product. And others seem to be that's either impossible or maybe not cost effective given what state they enter.
Okay, so we talk about recycling. And so the main issue with recycling, if it's a thermoset material, it means it was cross-linked. You can't fuse it again. It's just stuck in this state. You have to burn it. Now, that's the case of epoxy. Polyesters are that way. And they are used, a lot for composites. So composites, it's not only the issue that you have the glass reinforcement to deal with, but the resin itself can't really be recycled. The thermoplastics, you can remelt them. Now, the issue with recycling plastic is their densities are all very similar. So when you start mixing things together, you really get something that is not all that strong in general. And if you have contaminants, they really don't help you either. So for making pipes, they still limit the amount of recycling that they put in the material, because the cost of the resin and the pipe is not that much as opposed to the whole installation. So the idea that you'll take a risk on a pipe that is in homes and then eventually starts to burst and leak is just not worth it. Trying to recycle for that. So I say that recycling end up normally as making chairs and lunch tables and things that you can be super big, super heavy, and not very high strength.
What about the crosslink that prevents you from reconstituting it? Or there's no chemical process to do that?
So that cross-link is as strong as the other bonds. It might be the way for us to think about it. So if you're going to break one, you're going to break all of them. Yes. It's a good question. You forced me to think here. You can use also the plastics for underground pipes. This is just for drainage. And you can see whether the issue, it's not round anymore because it's so soft that over time it's going to sag. So just the effect of the ground weight on the pipe is turning it into an oval. Eventually it can even collapse. So that's not very, very helpful and productive in a lot of cases. Here, this is just kind of a shield for the fan of a radiator in cars. So a lot of under the hood components are injection molded parts of plastic, nylon traditionally, but they made a lot of improvement. Nylon the properties are very sensitive to moisture, which is not a good thing. So there's been developing resins that will have a more consistent behavior, whether you are in a dry environment or a very wet environment. So that's been a significant improvement there. So what happens when you deform the plastic? Let's see. I already brought this one, but let's do it again. So it was transparent. Let's see what happens. It just turned whitish. And you see that a lot if you, the old clips for the bread, they color the different things. I don't know. I hope I'm not that old that these don't exist anymore in your generation, that I didn't realize it. But the little clip with the hole that you just put to hold the bag of bread. No? Yes? 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 Good. So that plastic clip, if you just fold it, it's going to lose its color, right? It's turning white. So that's called stress whitening. And at the small scale, what it means is you have craze formation. Crazing is essentially a bunch of microvoid that form, but the whole clip doesn't break. In this case, this completely broke. It's a relatively brittle resin. But a lot of times, including, and this is very common with polypropylene in services, if it's wet or if the loading rate is a little higher, you start forming these voids, but you have what we call fibrils. So there's still a connection between one side and the other side of the crack-like feature, so it's still carrying load, but it's not as strong as it used to be, right? So just to relate to what we were talking about, the spherulite and how the deformation starts, this is a visual view of craze formation in a very thin film, so that it's a little difficult to make this on a large sample and visualize. But so let's say you have a spherulite right here. You can see that the craze, they all kind of go through the center of that spherulite, and that's because it's in this zone where the two crystals are parallel. We stretch them, and there's a lot of hydrostatic tension. Yes?
I'm confused about the whole spherulite thing.
Yep.
So normally when I envision a polymer, I think of the long strands of like spaghetti.
Uh-huh.
If it's a thermoset, it's just the spaghetti, and if it's a thermoset, so it's a thermoplastic, or yeah, it's just the spaghetti, and then if it's a thermoset, it has like the cross links.
Yep.
So where do the spheres, where do these, the sphere-like, like
Come into play? Yep.
Where is it in the
Yep.
spaghetti? Like, I'm
All right.
kinda confused.
So the question was about the difference, the really difference, where did the spherulite come in? And the main answer is it's when you go from melt to a solid. And what happens with polymer, though, it's not a very, very neat transition in a sense that if you heat up polymer, it doesn't come just like water or like liquid steel. Liquid steel is very fluid. A liquid polymer is going to be somewhat viscous, and you cool it down, depending at the speed that you're cooling down, it's influencing when you're going to start forming these crystals. So it's all a spaghetti, and then you cool it down. Eventually, you reach that point where there's a local organization starting at the nuclei in the spaghetti, and then it just spreads in different directions, just a little bit like what we talked about, ice formation or snow. It starts from the middle and goes in different directions. So depending on how fast you're cooling, that organization is going to take place at different rates. But essentially, the parts of the spaghetti that you have will sometimes be in the crystal zone or in between. You can't really move the entire spaghetti. If it's all mixed in, you can say, oh, you're going to be the crystal. So what happens is there's a little bit of organization of all these chains that fold back and forth to form that crystal. I hope I have a view of that. Yes. So see here, it kind of folds back and forth. So some of this is going to be one spaghetti piece. Some of it is going to be another one. And where you have the knots, you just put that in the amorphous zone.
So
I've never seen a good video of it, but I think you can visualize. It's all disorganized, and you start organizing with a little piece at a time and have this little layer that is organized. And to do that, the easiest way is you just push away the parts you don't like, everything that is too mingled to be connected.
okay, so the pom-poms are like interspersed throughout the spaghetti.
Yes, yes, yes. And that's so. If you wanted to trace here one of these long macromolecules, it could probably just start right here and go across between crystal and non-crystal. Yes, that's exactly right. Now, I'm exaggerating. Maybe one chain can go 2 crystals in one amorphous zone, maybe 3, something like that. But then that depends on molecular weight. You can probably start seeing a very nice effect of that crystallization. It's a little bit like acting like cross links because it's tying one piece in as part of a network. And that's why the polymer gets a lot stronger when it's starting to crystallize, because now it's a composite at the microscale. And these organized zones essentially have lower energy, but you can't crystallize the whole thing because you have all these other interaction that is stopping you from leading to a complete large crystal. If we were to cool it down very, very slowly, we get bigger crystals because we give ourselves more time for that organization.
So the spherulites are crystals, or
No, it's the overall organization that it's the spherulite is this whole thing that has hundreds and hundreds of crystals organized in such a way, and they connected to each other, just like the grains in the steel that we were looking at last time. Because as it's happening here, it's also happening on the next site, and eventually they get to each other. And it is a little bit of a weak zone. So between the spherulites, sometimes that's where it breaks because it's not as reinforced. Let's put it this way. All right. So now that may make more sense, right? So you have these crystals, and the parts that are oriented this way, when you spread, you get a little bit of hydrostatic tension between them in the amorphous zone. And because essentially the crystals are stiffer, they don't contract as easily, and that's where you can have the formation of these crays. And they don't break because you still have chains that go all the way across that crack-like feature. So the reason why this is resisting load is at the molecular level, there's a molecule that's over here, it goes over there, and it's connected on the other side. So it's still holding things together, and that's why it survived 1,000% strain or something like that. It became about 10 times more elongated than it was. So related to that, I do want you to know we don't really break these chains easily. So in all that deformation, it is ultimately sliding as opposed to actually breaking. So it's different with epoxy. With epoxy, you just eventually have to say, hey, I'm going this way, you're going this way, and that's it. So it's it's a characteristic of the thermoplastic that makes them very useful. They have pretty good toughness for their weight. So you can now probably make a lot more sense out of this little schematics. What we're doing here is we're looking at these crazes at a more refined scale. So this is a fibril here, you have another fibril there, and then you have to decide at the tip there which way you're going to go. So in terms of crack resistance, the main driver for a slow crack to continue in a polymer or a craze to grow and eventually break is the molecular weight. And we'll go through that a little bit more later, but hopefully with our discussion of the spaghetti that is long, that makes part of a, essentially micrometers of scale of travel, hopefully that appeals to you a little bit. So we'll go back to that, and for now we'll talk about just another mode that you can break. This is an interesting image, isn't it? We call that shear bending. What happens in shear bending is, first of all, it happens in bulk metallic glasses and amorphous polymer like the polycarbonate is a good example. This was done in polycarbonate. So when you start sliding in the polycarbonate, it creates a little bit of free space. In other words, to start that sliding, you have to create a little bit of an opening in the structure. And when you do that, you give room for more sliding. So there will be condition essentially where the strain is going to localize in these structures. And that's really what you're seeing here. So it's at the tip of a crack. The crack is propagating this way. So when it's at this slant, right here, you have a lot of shear on each side that is stopping the crack. And that's why polycarbonate is just very, very tough to the growth of cracks, because it's absorbing a lot of energy at the crack tip through this shear bending process. Now, if we're here, eventually we'll move up. When we consume all the energy, especially if it's a cyclic load or if there's just plenty of power to keep opening the crack, it's going to continue to grow. But it's one of those features that is just very, very different than the crazing that we were talking about. If you have a craze in the material and you're starting to form void, yes, you are absorbing energy to create that 1,000% strain, and hold the structure, but the next step is to keep going. There's no really back and forth. And here, so you can blunt the crack a lot more by deforming it in the two different directions. That's why you get a lot more toughness in this case. So on the two material we had, the one that, if you remember, we had to bend back and forth, I didn't bring it back, but it was the polycarbonate. Very, very tough, very, very deformable. Even if you put a notch in it, it gets this mechanism to blunt the crack and allow for a lot of deformation. And really, one of the main reasons is you don't have the spherulites and you don't have the crystallites in there to affect your behavior. All right. So what's the problem with plastics, guys? Why are we not using them all the time for everything? Tell me. It's not price, by the way. Yes. It will deform. So if you're thinking about a long-term load, like the pressure in a pipe, the weight of a building, I mean, everything, essentially, the frame of a car, it's a sustained load or a repeated load, and that causes the material to creep. So why does it creep? Somebody else, by the way. Why do plastic creep? There's a very, very simple answer. We're using them close to melting point. A lot of movement going on. So by basic principle, that's something I'd like you to remember. The temperature where you start to have creep is half the melting point. This is in Kelvin. So if we're thinking about steel, and I skipped that part because I just wanted to give something interesting that was different today. If we're thinking about steel, steel melts at 1600 degrees centigrade, so 1900 Kelvin, 1000 Kelvin, which is about 700 centigrade, it's going to start to creep just like the plastic, but most of the time we don't care. It will matter if we're building an engine, for example, but with respect to just a structural application, that's fine. It will matter if you have a fire. World Trade Center that we were talking about, so there's going to be a point where it's becoming softer, and just under sustained load, it's just going to start to creep by a number of mechanisms. Now, because we're talking about plastic, the main thing that happens is this starting to have this movement. If you put a GPS on the different chains, they're not where they were at the beginning, is what's going on here. It's not just a random fluctuation, elasticity. You start having a movement between them. Just to try to appeal to it, and that, to me, helped me when I was thinking about plastic, is we're talking about, putting some GPS on the center of gravity of these molecules and then say, well, it changes. If you reheat it sometimes, it will go back to this original location. And that is because if in the grand scheme of things, maybe I've been able to move one past the other, and that gives me my strain. But overall, they still are very entangled. So entanglement is a term used a lot thinking about all these macromolecules. Yes?
So on my bike, the chain creeps, right? So like on the bike, the chain gets longer with time.
Yeah.
And probably steel, right?
Yeah.
So what's up with that?
Okay, I'm trying to be fair to the video people. So the question was, why would the length of a chain on a bicycle increases over time? You are talking essentially about more the joints. So there's going to be different components. You have the two little links, and then you have all these things. There's a little bit of wear. So that it's going to give, and it's more of a fatigue phenomena or wear phenomena than the metal actually. So essentially, locally, in some parts of those links, you'll reach the yield strength in certain condition, like you switch gear, it just twisted. You do something the other way, but it is not the metal itself. So that becomes, creepy, and all that stuff. So you have to think about the real engineering definition of creep is essentially a temperature-activated phenomenon as opposed to an assembly phenomenon. Thank you. That was a good question. And same with my phrasing is more obvious.
Creep is a temperature.
Yeah. Now, can you make a scientific experiment and come back and tell me it can happen at 0.4? Of course, but this is the rule of thumb that we use for engineering. Okay, so all this is showing here is if you're thinking about a pipe that's going to be used for a very long time, well, when you test in the lab that you're going to do in 1 hour, gives you, let's say on this one, it gives you 6 megapascal or 7 megapascal of strength, but if you waited and you ran your test for about 4 months, there will only be 2. That's a factor of 4. So, and that's actually how a lot of the design of these structural plastic is done, is you accelerate the temperature a little bit, and you give them about a 4-month period of testing. If you try to do it really quick, if you heat up too much, a lot of times you change the phenomena of deformation. And so that's where there's always a limit in the accelerated testing. I'm sure you've heard of time temperature equivalent and all those sorts of things, and I'm actually not going to spend a lot of times on that but I do want you to remember, if somebody says, oh, yeah, I'll let you know if this plastic's going to be good for 50 years. Okay, well, good luck to you, because the minimum, I would say, is a 4-month test. And even there, you will be benchmarking against other material of a similar nature that have been tested 4 months, but also been in service for 20 years to know whether or not there's this special phenomena that changes over time, even chemical degradation, UV. There's a lot of things that can happen over time. So we really here are just focusing on the basic stuff. And there are a lot of standards on how to do this. So one last concept that will appeal to you, hopefully, and go back to this initial discussion today about the stress strain curve. We're looking at the effect of molecular weight on the time to fail. So over here we have the load that we're putting on, and we're putting the load, taking it off, fatigue loading. So it's just all cycling. And looking at the number of cycling that causes the failures. So let's say with 15 megapascal, you can see here it's 10 to the 4 or 10 to the 7. Isn't that nice? One lasts 1,000 times longer than the other, and it's just because of molecular weight. And I know you can understand this, and hopefully you'll remember it too, that it's all about, am I able to move one big chain with respect to the other? If they're a lot shorter, yeah, it's a soup. You know, if it's longer, well, it's a spaghetti that's frozen, something like that. So try to think about that, and then think about what happens on the other hand if you are doing a tensile test. So if you do a tensile test and you have all these ferrites, for example, what you can see with respect to molecular weight is there's going to be a point, right here. So the strength as a function of molecular weight is this curve. You get to a point right here, and I hate when people do these curves. I mean, the curve doesn't reflect the data. From here to here, the strength is going down with the molecular weight. Can you think of a reason for that? We have to go back to the spherulite to explain it. So with the spherulite, if you have more molecular weight, it's harder to form the crystals. So you get typically less crystallinity for the same condition when you have more molecular weight. So less crystallinity means over here less strength. It's easier to deform it in the pool test. Does that mean it's weaker for service? No. Typically, it's the exact opposite. So essentially, the idea that you would compare plastics using the tensile test as an idea on how they're going to do in service doesn't quite work. The better way, just so you know, to get an idea of molecular weight, it's very hard to know. There's no really easy probe for that, but we look at the melt viscosity. So at a certain temperature, you just slide it through a given opening, depending on flow rate. So the viscosity of the resin at a certain temperature above the melting point is a good indication of molecular weight. So that's used for process control, and it's included in plastic specifications that we'll go over very quickly. I think if you guys have questions, I had some application. We can go over them at another time. I don't want to take too much time. It's different, isn't it? And thank you so much for the questions, by the way, because I know I can be a little jumpy sometimes. I try not to, but anything that wasn't clear, I want you to remember only 2 or 3 things, right? Spherulites, molecular weight, and I guess you have different mechanism of failure. You can have crazes, shear bending, or just regular deformation. And that's always the funny thing. Like I'm showing you the stuff you can see. A lot of times, the polymer is going to deform without showing anything really in the microstructure, and that's kind of what we want. You know, crazes are not all that cool for service, but they will eventually happen. This is what we have to remember. Well, thank you so much.